Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here with another video here on ZyBooks Section 2.2 titled An Introduction to Proofs. So this section is a very basic introduction with lots of definitions, as you get with most introductions to things, and some very simple examples. Now, if you recall, if you took a geometry class before, remember how they did, you did like some T-table proofs where you had on the left side a statement, on the right side, a reason for that statement. Well, that's kind of what we're doing. That's what a proof is. You try to show, using some basic definitions and things called axioms, which are things that are assumed to be true, and using previously known true statements, you can go through, and keep stating true statement after true statement after true statement until you reach some final conclusion that you're trying to show. And every time you state something, you also have to state a reason for it. Right? And you can do it with like a T-table, like in geometry, or as you're going to see here, written out in full sentences. Right? Okay, so again, I'll read the opening to you. A primary endeavor in mathematics is to prove theorems. A theorem is a statement that can be proven to be true. Right. A proof consists of a series of steps, right, each of which follows logically from assumptions or from previously proven statements. Right? So you use some assumed truths and some previously known truths to help you out, whose final step should result in the statement of the theorem being proven. So you have statements and your steps, and with each step should be some reason for that step as well. The proof of a theorem may make use of what are called axioms. Right, axioms are statements which are assumed to be true. Okay, so some really basic stuff that you're assuming to be true without actually showing to be true. A proof may also make use of previously proven theorems, right? If you know something else is true already, you can use that. You can use anything that you know is a truth to help you reason out in a proof. Although mathematical proofs are typically expressed in English, the formalism of logic provides a good foundation for mathematical reasoning used in proving theorems. A proof should read like a verbal argument, right, designed to convince a skeptical listener that the assertion is true. Right? So you do have to keep in mind who's reading your proof. Right? Now, since you're a beginning, you're doing a beginning of proofs here, an introduction, you should be assuming that someone who has no idea what's going on is reading your proofs. And then you have to go step by step, explain to this person why a particular statement is true. Right? You have to be like they said, like a verbal argument. You're trying to convince someone that something is true or that something is false. You can also prove that something is false. In computer science, proofs are important for establishing that a program works as expected, showing that a crypto system is secure, or validating a set of inferences in artificial intelligence, to name a few. Right? So here's a theorem. Now I'm going to write out a proof for this theorem on a piece of paper to show you what I would be expecting to see in a formal proof of a statement. So they're calling it a simple theorem here, but theorem 221. Every positive integer is less than or equal to its square. Okay, so I've started off, I've written the theorem. Right, that says every positive integer is less than or equal to its square. Now, something I like doing that you don't have to do all the time, but I like to let's write the logical. I'll write this theorem in logical symbols, right, with quantifiers and variables and everything like we've seen in chapter 1. So first, what's the domain here? What is this statement about? Right. The statement is about positive integers. I'm noticing, right? The only type of object mentioned in this statement is a positive integer. So the objects, the object mentioned in the statement is about positive integers. All right, so I'll say that's the domain. Right? The domain is the set of positive integers, 1, 2, 3, and so on. Right? All right, and then I'm going to restate the theorem in logic notation. All the stuff we saw back in chapter 1. So this is saying every positive integer is less than or equal to its square. So the every is a key word there. So for every single one of these, remember this upside down A, for all these integers, for all, I'll call them x. Right? For all, x represents any positive integer here. The following statement will be true. For every positive integer, that positive integer will be less than or equal to its square. So x is the positive integer here. X will be less than or equal to its square, right? So x squared. So here would be a way to write that same statement in English using our logical symbols from chapter 1. Right. So this is a universal statement. Right? This is definitely a universal statement. It's about every positive integer. All right, so I have the theorem stated. Again, this is kind of optional stuff here, where where you state the domain of the problem and whatnot. I'd say this was optional. You don't have to write out the domain, and you can just think about it and think about how to express it in logic. And then beneath the theorem, we're going to write out the word proof to indicate that the proof is starting. Right. Now, to prove a universal statement, right? We the domain here. We have to prove that this is true for every single positive integer. Now, you can do some scratch work, right? So I'm not writing the proof yet. What I'm going to do right now is some exploration. Exploring. Trying some stuff out, right? This is not the proof. Right? This is not the proof. But let's just see if we believe this, right? Do we even believe that the statement is true? Because if you don't even believe it's true, if you don't see that it's true, how can you go about proving it, right? Or maybe we'll get lucky and find a counterexample and show that it's false. I mean, this isn't false, but so if I go through, is 1 less than or equal to 1 squared? Yes, that's true. Is 2 less than or equal to 2 squared? That's true. 2 is less than 4. Is 3 less than or that's 1 is equal to 1, 2 is less than 4. Is 3 less than or equal to 3 squared? That's true. So I mean, just based on the first few here, it looks like this is a true statement, right? So it feels true to me, right? So I go back and I try to, get into the proof. Now, to prove a universal statement, right? Again, I couldn't do what I was doing on this page all day long. You can't possibly show that it's true for every single one of them. There's no way. There's infinitely many values in the domain. So instead of going one at a time, because you can't do that, that would take forever. That would be an infinite amount of time. We're going to do what's called universal generalization. And this comes up later in the section as well. Universal generalization. I'm going to start off with that. This is to prove that a universal statement, about an infinitely large domain, to prove a universal statement about an infinitely large domain is true, you use what's called universal generalization. Where basically, I'm going to start off the proof saying, let's suppose, or let's let some random letter, right, some variable x, represent an arbitrary value of the domain, right? It could represent any value from the domain, and that way we're talking about the entire domain. Let x be an arbitrary positive integer. Okay. So I go from having infinite limiting to letting one variable, one expression represent everybody from that domain. Right? That way That way we can talk about everything from the domain. We can generalize everything from the domain without actually going one member at a time. Right. Okay. Then come our statements and reasons. Right. In any proof, like I said earlier, like in a geometry proof, you're going to have statements and then reasons for those statements. And every statement I write should be something that is either assumed to be true, something that we know to be true, or something that we've shown to be true, a theorem from earlier. Right? But what we're going to keep doing is writing truths. And I keep writing truths that follow from one another, and using things from the past that you might know in axioms and other theorems, until we finally get to this statement here. Right? I wrote it in logic for a reason. This is what it means for it that integer to be less than or equal to its square. All right, so use some definitions. Right? Use definitions, use axioms, use truths to work your way through. And eventually, I want to end up with this statement here. So x is an arbitrary positive integer. So what does that mean? All right, that means that or I guess since x is positive, that means that x must be greater than 0. All right. Now you could write x is greater than 0, and then over here x is positive. You have a statement and then a reason. Statement and reason. But here I have my reason, then a statement. And as long as you have the reasoning behind things written down, it should be good. So since x is positive, x is greater than 0 also is a positive integer. Right? Since x is a positive integer, and we can see it in my list up here, not only is x greater than 0, but we can go a little further. All right, so since x is a positive integer, you see from my list, the positive integers are all greater than or equal to 1. We could even go further with that. And now I'm working with this inequality. X is greater than or equal to 1. And do you see how if I were to just multiply both sides by x, I would get this statement here, right? Just flip it around. And I can do that because of the fact that x is positive, right? Statements about inequalities we know to be true. Remember, a statement you should know about inequalities that's true is if you multiply both sides of an inequality by a positive number, right? The inequality doesn't change. So, since x is positive, and maybe I could have written that after, right? But since x is positive, we can multiply both sides of x is greater than or equal to 1, because that's a true statement. Right? We can multiply x is greater than or equal to 1 on both sides by x, and the inequality will not change on both sides by x, yielding or producing the following. You'd have x squared on the left side, and it is greater than or equal to x on the left. Or, if you just switch sides here, x is less than or equal to x squared. Therefore, now you're going to see some notation sometimes. Like if you see this thing with the 3 dots ever in a textbook, this just means therefore. Right? Therefore, every positive integer is less than or equal to its square. Because remember, x is representing an arbitrary positive integer. X represents every positive integer. So what we have here is a statement, therefore, and then we restate the theorem. We restate what we're trying to prove. Every positive integer, which is what x represents, every positive integer is less than or equal to its square, right? X squared. Right. So, and you finish with what you were trying to show, right? Start with something basic, keep writing truths, keep writing true statements and reasons, and finish with what you were trying to show and state that. And then to indicate that you've ended the proof, some books you'll see the letters Q, E, D at the end of the proof, which is short for the Latin quod erat demonstratum, like what we were trying to show or something like that. This ends the proof, QED. You might also see in some textbooks just a little box, might even be filled in, okay? But there's some way to indicate that you have ended the proof after stating what you're trying to show. So you see, it can take a bit of time. Right? It can be a little tedious, especially since you're going to be writing out your reasons. Right? But you need to have true statements with reasoning, statements, reasons, and so on. Okay, until you have shown what it is that was being stated in the beginning, what the theorem was. Okay. All right. So, and again, they have this animation here where again they tell you, and you can play it if you wish, but see, state the theorem to be proven. Then I wrote the word proof, right? Indicate that the proof is starting. Then this was that universal generalization, right? This is a universal statement. It's about every positive integer, so you can't possibly show them all. So you let x represent an integer, right? And it should have just been a positive integer here. This is a statement about the positive integers, but where x is greater than 0, right? Indicating that it's positive, right? You just take what's given to you. So you name an arbitrary object in the domain. Again, this is only for universal statements with domains that are infinitely large. You name an arbitrary object, say x or y or z, and then state reasoning in complete sentences. Now, when you're doing a proof for me, if you write like a geometry proof where you have a statement and then a reason next to it, that'll be fine too for me. But in most books you're going to read, if you continue on in mathematics, most mathematical proofs are written in complete English sentences or whatever language they're in. So through the reasoning, right, with proof, and then now I think they should have at the end here also stated what they were trying to show. They say, hey, look, therefore, every positive integer is less than or equal to its square. Right. Like I did, but they ended here and they say, oh, you can clearly see that the theorem is true. That's what we were trying to show. And then you see the little box there, the little filled in square. That's the end of proof symbol. So again, you're seeing that or QED or whatever symbol an author has. Some authors have different symbols for endings of proofs. But yeah, so and this is what's called also a direct proof. We're going to get into other sections later on different proof methods. This is a very simple version of a direct proof where you just start with some value of the domain in general if it's a universal statement, and then work your way forward directly to the statement in question and directly to the proof of the theorem. We'll see other versions of proofs called like indirect proofs, proofs by contrapositive, proof by contradiction, proof by cases. We'll see lots of different proof methods in the coming sections of Chapter 2. All right, but hopefully you got the structure of a proof down. Right, even though it's a simpler proof, the structure of the proof I have written here, that should be the way you structure all your proofs. You state the theorem, state what you're trying to prove, you could possibly write the domain. You don't have to do this. Notice they didn't do that, but write the domain. What's the statement about? All right. What's the domain of the statement? Or there might be multiple domains as well. They might be talking about multiple things. So you can have multiple domains. And then maybe you could translate it into logical notation. Again, that's not really necessary. Then you state when indicate that the proof is beginning. Then you make statements and reasons. Statements and reasons. Things are given. Things I know are true. Keep right until you get to what you're trying to show, and then make sure you indicate that the proof has ended. All right. So you can wait through that. And then here's some examples where we have some nested quantifiers where they give you some examples of theorems, statements that can be proven true, and then the logic, written in logical symbols. So here's a couple. Here's another one. There is they have a statement in English, and then that same statement in logic. All right, as I did with the theorem on the paper I had earlier. And this will be something good to know. A number n is a perfect square if n equals k squared for some integer k. Right, so there's another definition that you can throw onto the definitions from section 2.1. Remember the definition for even integer, odd integer, prime number, composite number, divides, rational number, all that stuff. Add on to that the definition of what does it mean for a number to be a perfect square. All right, so let's look at these. For each statement, we're asked to indicate whether the statement is an existential statement. There exists, there is one, there is at least one, or a universal statement, right? For every, for all pairs, and so on. The product of two negative real numbers is a positive real number. So think about that. Are they asking for two specific negative real numbers? Are they saying there is a pair of negative numbers whose product is positive? No. They're not saying there is a pair of negative numbers whose product is positive. They're saying all pairs, right? The product of any two negative numbers is positive. So this is definitely a universal statement. Number two, there is. That's the dead giveaway right there. There is a perfect square. That is the sum of two non-zero perfect squares. They're not saying all perfect squares are the sum of two non-zero perfect squares. They're saying there is, right, existential, and I'll leave the third one to you. All right. Now, I already mentioned universal generalization in my proof earlier. We're getting in here in this part of the section to proofs of universal statements, statements like for all and whatnot, for every. Now, if the domain is small, right? Look, if the domain of a universal statement is small or has only so many values in it, is finite, not infinite, you could go through every value in the domain one at a time until you have proven the statement for all of them. All right, they give you an example here. So I'll show you this here in the participation activity. All right, so I'll write this out and get back to you. Okay, so here's the theorem that was written. It says, for every positive integer n less than 3, this statement, and n plus 1 squared is greater than or equal to 3 to the nth. So like I did earlier, again, me personally, I like to talk about the domains of the problem, what objects are being talked about. Well, they're saying this statement is about every positive integer less than 3. What are the positive integers less than 3? That's just 1 and 2. So the domain of this statement, I mean, sure, it's for all. All right, the statement in logic, if I write it in logical symbols, is, for every value in the domain, say it's called x, this statement is true. X plus 1, I guess I should have called it n, huh? N plus 1. For every value n in the domain, n plus 1 squared is greater than or equal to 3 to the n. there's that statement in logic where, again, the domain is just, every positive integer less than 3, just the numbers 1 and 2. So for the proof, I don't have to do that universal generalization like I did in the last statement, because this time the domain is not infinite. It's still a universal statement, right? It's still a for all, for every. So I still have to show that this statement is true for every value in the domain, but there's only 2 values in the domain. So proof, for n equals 1, you plug it in. 1 plus 1 squared is equal to 2 squared, right? That's equal to 4. And 3 to the 3 to the first is equal to 3. So, we have 1 plus 1 squared is greater than or equal to 3 to the first, right? This statement is true. This is, again, 4 is greater than or equal to 3. This statement is true for n equals 1. Then, for n equals 2, at the only other value in the domain, we have, 2 plus 1 squared is 3 squared, that's 9. And 3 to the second is 9. So we do have that statement, right? 2 plus 1 squared is greater than or equal to 3 to the second. They're equal. 9 is greater than or equal to 9, right? It satisfies the equal to part. Therefore, for every positive integer less than 3, I'll just say therefore the statement is true. Okay, because I'm out of room here, but the statement is true. Little box there to end the proof, or QED. Normally, I would write out the statement, therefore, for every positive integer less than 3, n plus 1 squared is greater than or equal to 3n. But yeah, there's only 2 values in the domain. This is called a proof by exhaustion. All right, a proof by exhaustion, where you're able to go through and actually show that the statement is true for every single value in the domain. All right, proof by exhaustion. Now, this isn't going to always happen, right? You're not always going to be able to do universal statements by exhaustion, because most of the stuff we're going to see, the domain will be infinitely large, right? So there's no way to do proof by exhaustion in those cases. All right, so I just did that. That was this one here, right? The 2 cases. Right. This is what I did earlier. Universal generalization. All right, when you have a universal statement, like, and they're showing it here, right? Like that one earlier, every positive integer is less than or equal to its square. The domain here is all positive integers. There's infinitely many of those. And it's a universal statement, right? You got every. In universal statements with infinitely many values in the domains, you're going to be doing generalizations like this. You're going to say, hey, I can't possibly go through exhaustion. I can't go through every single one. So I'm going to let a variable represent every single one. Right? I'm going to let x be a positive integer. And there you go, like I did earlier in my proof. All right, and they define what, hopefully you know what it means for 2 integers to be consecutive, right? It just means 5, 6, 6, 7, 7, 8, they're 1 apart. All right, so now they're asking, can you do this universal generalization, right? Let some letters, let some expressions represent general things, right? Represent values of your domains. So the average of, so this statement here, the average of 2 real numbers is, less than or equal to at least one of those 2 numbers. So what would be a valid beginning to this proof? And then, then you have, so all we're asked to do here is begin the proof. All right. So what is this about? This is about real numbers. And it says the average of 2 real numbers. So I'm going to start off wanting things to represent 2 real numbers. So let x and y be 2 real numbers, because again, the real numbers is the domain here. You can't possibly go through every single real number. There's too many. There's infinitely many. But I can let, say x and y be 2 real numbers. Now all three of these start with that. So that's a good start to the proof, but then what would you be trying to show? You're trying to show that this statement is true, right? That the average of two real numbers is less than or equal to at least one of those numbers. So you add them up, divide by 2, right? The average is less than one of them or less than the other one, or less than or equal to the other one. So this first part, I'd start with this statement, let x and y be two real numbers. That's my universal generalization. And then I would write down steps showing that the x plus y divided by 2 is less than or equal to x plus y. Is this statement? No, it's not. This is the average of the two is less than or equal to the sum of the two. That's not what this is saying. The second one, steps showing that x plus y over 2 is less than or equal to x, or x plus y over 2 is less than or equal to y. This is what this is saying. This is saying the average is less than or equal to one of them or the other one. Right? The average is less than or equal to at least one of the two numbers. So this is how I'd construct the proof, or at least how I'd start it. Right? They don't show the steps. Right? They don't show the steps, but again, the point of this section is to introduce you to starting proofs and proofwriting, and we'll get into actual more writing of proofs, more completely writing of proofs in sections after this. The difference of two odd and I'll skip that one and go to this one because this one's a little tricky. Let's do all three. Why not? Sorry. The difference of two odd integers is even. So this is about the integers, right? And it's specifically about two odd integers, right? I want to talk about the difference of two odd integers. So again, the odd integers are 1, 3, 5, 7, 9. There's infinitely many of them. So I need to generalize, represent them with some letters. And I want two of them, right? So, suppose x and y are two odd integers. That would be a great start. So this is great. I wouldn't want to suppose that x and y are even integers, right? The statement's about two odd integers. So not that one. Suppose that x and y are integers and that x minus y is even. No, you cannot start with what you're trying to prove. This is saying the difference of two integers is even, not two odd integers also. So it's this first one, right, where I would suppose that I have two odd integers, and then I'd write down steps to show that x minus y was even. Right, the difference between them was even. I want to end with, not start with, end with the difference being even. All right, one more here. Among any two consecutive integers. Now, two consecutive integers. Now, the word consecutive is important there, because if I'm talking about, again, the domain here is the integers, right? And but we're asked to start off with two consecutive integers, right? Not just any two old integers, because they have to be one apart. So do you see how this first one would actually be not a good start? If I just let x and y be two integers, that's not really representing two consecutive integers, right? Because one of them could be 5, the other one could be 9. Those aren't consecutive, right? And these represent just general integers. I would say just let one be an integer. If you know what one of them is, right? So just let x be an integer. Then you'll know what the consecutive one is, right? The consecutive one would just be one more than that, right? If x is an integer, x plus 1 would be the consecutive. And they're saying among any two consecutive integers, there is an odd number and an even number. So if I let x be an integer and then go through some steps to show that one of them's odd and the other one, x plus 1, see, consecutive, is even, that would be a good way to start. And then again, they don't have the steps here, but we're going to go through again writing out steps and fully doing proofs in future sections. Oops. Oh, there is an odd number and an even number. So all right. So yeah, what if I chose x to be 6? All right. So you have to show one is odd, one is even, or one is even and one is odd. Yeah. What if x were 6? I wasn't thinking. Sorry. Okay. But still, I would let x be an integer to start, knowing that the word consecutive was in there. So I don't need to do a y, right? If I know x is an integer, right, then x plus 1 would be consecutive. And show that 1 is even or 1 is odd. You have to go through both cases. Okay. We've talked about counterexamples before. When you have a universal statement, a counterexample is just an example that shows that it's false, right? It's an example that shows that a universal statement is false, and they define that down here. All right. So just go down here to some of these universal statements involving the real numbers. And this, they say just provide a counterexample. So look at this first statement. For every real number x, 7 times the absolute value of x is 7. Well, if x were 5, that would be false, wouldn't it? 7 times the absolute value of 5 would be 35, not 7. So x equals 5. Now, 5 is not the only counterexample, but it's the only one they listed. X could be 3, 2, 8, negative 10, and it would also make this false. All right. Just of the ones that were listed, 5 is a counterexample. For all real numbers x is not equal to x squared. Well, of the ones that are listed here, 1 is not equal to x squared. That's not true. 1 is equal to x squared. So negative 1 is not equal to negative 1 squared, right? Negative 1 squared is positive 1. Negative 1 is not equal to positive 1. That would make that true. So 1 is the one that makes it false. Right? Negative 1 actually makes this statement true. 1 makes this statement false. Right? 1 is equal to 1 squared, and so on. Right? You can do the last one, obviously. Counterexamples for conditional statements. Right? Conditional statements are if-then. Right? We've talked about conditional statements back in chapter 1. Right? Implications: if this, then that. So, a counterexample for a conditional statement must satisfy the hypotheses and contradict the conclusion. So, if you have a universal statement with an implication, if H then C, a counterexample makes H true but C false. Right, therefore, making the whole implication false. So let's identify some counterexamples here. So for each statement, select the values for the variables that are a counterexample to the statement. All right. So this is for any real numbers x and y. If x is less than y and y is greater than 0, y is positive, then x squared is less than y squared. So for a counterexample of this, I need to find values that make this true. I need an x that's less than a y and a positive y, but I need this conclusion, x squared is less than y squared, to be false. All right, so this can't be a counterexample because y is not positive. It doesn't satisfy the hypothesis. This can be, right? X is less than y, y is positive, but the conclusion is true though. A half squared is a fourth. 1 squared is 1. A fourth is less than 1. So the conclusion is true. This would make it true, actually. This is good. X is less than y. Y is positive, so it satisfies the hypothesis. And 1 squared is less than 1 squared. That's false. 1 squared is equal to 1 squared. So this is a counterexample, right, to show that this statement is actually a false statement. This is not a true statement. And you can do this on your own, number 2. All right, so that was all about universal statements, right? Proving universal statements are true. You can do it by exhaustion if the domain is small enough, right? If the domain is finite, or through universal generalization, right? And that's if like the example I showed you earlier, where you let variables represent arbitrary elements from the domain. All right. Now we're proving existential statements. There exists, there is at least one. A proof that shows that an existential statement is true is called an existence proof. The most common type of existence proof is a constructive proof of existence. All right. This is where you actually find an example. A constructive proof of existence just gives that example of an element in the domain or a set of directions to construct an element in the domain that has the required properties. All right. So they give you an example here of a constructive proof of existence, where again you just to show that a existence proof, to show that an existential statement is true, right? You only need to find one value in the domain that makes it true. So these constructive proofs again just show you, how they actually find that value in the domain for you and show you. There are also non-constructive proofs of existence where it just shows you that the element must be there, right? It just demonstrates that there must be an element in the domain that satisfies the property that satisfies the statement, but it doesn't give you specifically what it is. All right. And you may have seen you've seen stuff like this with the intermediate value theorem in calculus possibly, or pre-calc, whenever you saw the intermediate value theorem. Remember how you could use the intermediate value theorem to prove that a continuous function over some interval had a zero in that interval, right? If it was positive on one end and negative on the other, then there had to be a zero, at least one zero in between. That would be an example of a non-constructive, right? You don't find the zero, you just show that there has to be one. All right. So below is a list of true existential statements. Match each statement to the specific numbers that prove that the statement is true, right? To the example. There are two consecutive integers whose sum, is equal to the difference between the larger number and the smaller number. So, 4 plus 5 is 9, 5 minus 4 is 1, no. 1 plus 2 is 3, 2 minus 1 is 1, no. 0 plus 1 is 1, 1 minus 0 is 1. This is satisfying that statement. All right, and you can work with the others. All right. Now, disproving existential statements. All right, when I say there is, the opposite is there isn't. All right. So if I say there is an element of the domain that makes the statement true, the opposite of that would be there is not an element of the domain that makes it true, meaning every element of the domain makes it false. Remember how to negate existential statements with De Morgan's law. Right. So they give you some examples here. Let me just go to the participation activity again. You do the reading. Select the statement that must be proven in order to show that the statement below is false. So you're trying to show that this is false. There is an integer x that satisfies this property. X squared minus x equals 1. So to show that this is false, you'd have to show that the opposite of it is true. And what's the opposite of this? Now let me actually, I'll bring up a paper here, and we're going to write this statement in logic. All right. So there is an integer x. So there exists, let me get some better marker here. So there is an integer x. Right? There exists an integer x that satisfies the following: x squared minus x equals 1. Now they're telling us that we're trying to prove that this is false. Right? This is a false statement. In order to show that this is false, we would show that the opposite of it is true. So if I negate this, this would be a true statement, right? If the original, so we would have to show that this is true in order to show that this is false, right? Now, what is the negation of this statement? Now, remember the De Morgan's law. When I negate an existential, this is going to be this is logically equivalent to markers. This is logically equivalent to, remember, for all x, not this. Right? Move the negation inside here. Now another way to say not this, right, not x squared minus x equals 1 is saying that x squared minus x is not equal to 1. Right? You can say that as well. So saying there is an integer x that satisfies x squared minus x equals 1, saying that that's false is the same as saying that every integer x satisfies this, is true. Satisfies x squared minus x is not equal to 1. So that's the third one there. All right, and you see the correct come up, right? See. And I'll let you look at the last one. All right. Then you got the challenge activity. Starting to this one. All right. So introduction to proof. So suppose that the following fact is proven by exhaustion, right, where the domain have only so many values. Every integer in the range from 169 through 171 is composite. So select the lines that would be included in the proof. Well, from 169 to 171, so this line about 168 has nothing to do with it. 169, 170, 171, that's it. That was it's kind of a joke, that one. All right, move on, next level. Consider the following existential statement. Theorem. There are two prime numbers less than 14 whose sum is also prime. Now it's an existential statement. Now it's a theorem. A theorem means it can be proven true. And to prove an existential statement true, you just find one example. Just find one example of two prime numbers less than 14 whose sum is also prime. Well, let's see. 2 and 3 are prime. They're both less than 14. Their sum is 5, which is also prime. Hey. Select the pairs of numbers that show the exit. Now, that makes it true. But it wants you to select all the pairs. Like this would be enough. This would be enough to prove it. 2 and 3 make this true, but they're asking for all the pairs. 4 and 7. Now 4 is not prime. So no use in that one. 2 and 13 are prime. They're less than 14. Their sum though is 15, which is not prime. 2 and 5, those are prime. They're less than 14. And when you add them up, you get 7, which is also prime, so 2 and 5. 3 and 7 are prime. They're less than 14, but when you add them up, you get 10, which is not prime. So just those two. Again, you only needed to show, find one. When they say there are two prime numbers that less than 14 whose sum is prime, to show that that's true, you just need to find one pair, but they asked you for a couple. And you can do the last one. Again, you might be seeing different numbers than I am, or different orders of things. Right? Just the way you go about them would be the same. All right. Then you have your additional exercises, and some of these are included in your assignment 2. Others are not. You can check your solutions. Right? You can view the solutions, and please try, especially now with these proofs. I really want you to get used to some proof writing here. State the theorem. Write the word proof to let people know you're starting the proof. Then you write your definitions, statements, reasons. Every statement you write, everything that is true that you write that follows from the previous lines, everything you write down needs to have a reason. And it all leads up until the final statement, which is the statement of the theorem, right, showing that the theorem is a true statement. And then you write some little symbol, QED, a little box to show that the proof is over. Please do your proofs in a proper way, and try to do all these problems before you look at the solutions, because as I've been saying in every video, you're not going to learn anything if you just look at the solution and copy those down. And do the ones on the assignment, of course, with the assignment and upload that. But I would also recommend you practice the ones that aren't in the assignment, because that's the only way you're going to get better at this stuff is practice. And then you'll check the solution, see how you did. And if you still have any issues, of course, let me know. All right. So that's it for this Introduction to Proofs, Section 2.2. Thanks for watching.